recording on. So a few of you have submitted your exams. Most of you have not. So I hope everyone is well into the exam and is just double checking or finishing up the last few problems so that it to be able to turn it in by 5, right? Because it's due at 5 p.m. and so I don't want you to be late. So don't go past the due time. Okay. So try to get that in. But even if you haven't made substantial progress on the test, you would still have time after class because it's not that lengthy of an exam, I think. So you would still have time to finish it by 5 o'clock, except there's that issue of converting it to PDF that takes and then emailing it, that takes a few minutes. So you got to leave time for got to make sure you leave time for that too. Let's see, we don't have anything due today. We have this homework on intro to limits that's due Saturday, so be careful. That's due on a Saturday. I don't think that's too hard of a homework. This one might be a little bit more difficult. Evaluating limits analytically, that is, by hand with pencil and paper. I think this has more graphs in it, evaluating limits by using graphs, but this is mostly pencil and paper evaluation of limits, as we discussed last time. And we still have a few more examples that I'm going to show you today. We're not going to work through them step by step. I've already got them solved, but I did want to show you the solutions to finding a few more limits. So this may show up in couple of these may show up in the homework toward the end of the homework. And then we're going to go to talking about something that we've been hinting about since we started derivatives, and that's applications of derivatives, and in particular, this important application of derivatives of finding extrema. Extrema is the catch-all term for turning point. So extrema includes local minima and local maxima. So a local maximum would be a peak turning point. A local minimum would be a valley turning point. You combine those are called extrema, right? Extreme values of a function, and discuss what's called the first derivative test, which is just a process, kind of a systematic process of using the first derivative to locate these extreme values. But you already know really how to do this. It's just kind of putting it all together in kind of a single package. That's what the first derivative test is, right? And the key step of this is finding the key step of locating extrema is finding where the tangent lines have slope 0, right? Okay, so or where the derivative is 0. That's the main thing, and so we've talked about that several times, and so we're just going to kind of summarize that today, and then now. One of the fun things with finding extreme values are solving what are known as optimization problems, and so these are, of course, are practical applications of finding extreme values of functions. So I gave you a homework here for optimization, but this is extra credit, okay? And so it's not due until, I think that's the time of the final, the day of the final, but I will adjust this if that's not the correct day of the final. So it's not due until the time of the final. There's only, I think, 6 problems on here, and this is optional. So if you finish this with a score of 80 by the time of the final, then you would get 10 extra credit points on the final exam, right? So you would get a bonus on the final exam. And these are kind of fun problems. These are stated problems, applied problems that involve, again, finding maximum or minimum values of functions. And some of them
that is going to be for tonight or before the test, like 5 p.m.?
What now, Mohammed?
This is going to be due before 5 p.m. or before?
No, this is due on May the 11th.
Oh, okay.
Yeah, final exam, right? Okay.
Oh, okay. I thought
so we still have a third test and then the final exam, right? So this is a kind of a project, right? Kind of a long-term project too.
Okay.
Homework. You don't have to do it all at once, but you will have sort of the tools, the basic tools you need once, well, the basic tools at least, once we talk about the so-called first derivative test today, which is what we're going to do here pretty quickly. All right. So that's kind of where we are right now. Do y'all have any quick questions about anything that you want to know about? So I'll probably be talking a lot today, and so we may not have as much time for interaction because I want to cover as much of this first derivative test as I can today, and I still have to finish these few examples with evaluating limits. All right, so that we didn't finish last time. So unfortunately, I'm going to be talking more and faster than normal today. All right, so bear with me. Try to stay engaged, right, and pay attention to the work that we're doing. So of course, so the homework will be easier, and your preparation for test number 3 will be easier as well, right? Okay, so unless there are any quick questions here, I'm just going to launch right into the lecture on these topics. Let me switch to the notes here. So these are still the finishing up evaluating limits, and so I want to look again at some of the more exotic examples that involve some kind of little special tricks that you have to know of to evaluate the limit. You need to see some examples like this if these types of problems show up in your homework, right? Okay, so that you'll know what you can do to evaluate the limit if you recall the example. So let's start with this first one where we're trying to evaluate the limit as x approaches 4 of this expression. So that is kind of a little bit of a complicated expression, right? But even though it's complicated, it wouldn't be that difficult to evaluate this limit if this expression were defined at x equal 4. In other words, if you could just substitute 4 into the expression and simplify the arithmetic, then you have a 99% chance that the value that you get by substituting the limit value is going to be the correct limit. All right, because as we talked about last time, most of the functions that we're dealing with in the class, and most of the functions that you're going to be dealing with, in practice in general, not just in this class, but in other classes as well, those are going to be continuous functions. And so if you have a continuous function and you're trying to calculate the limit of that function at a particular number, as long as the function is continuous and that number is in the domain of the function, then you can just evaluate the limit by substitution. So the limit becomes, kind of trivial to calculate, right? So now this is a continuous function. So even though it's kind of an ugly expression, this is a continuous function. But unfortunately, the number 4 is not in the domain of this function. So that means the function is not continuous at x equals 4, because remember, the number has to be in the domain for the function to be continuous at that number, right? And see, when you plug in 4 into this expression, unfortunately, you end up with division by 0 because you get 4 minus 4 in the denominator, right? So that means that 4 is not in the domain. Now, oftentimes that means the limit is not going to exist. So turns out you won't have a limit in many instances in that situation. We'll see an example of that in just a moment here at the end of these examples. But I think there does exist a limit in this case, all right? And if we can make a graph of this expression, we could probably see that there really is going to be a limit to this this function, this formula, when x approaches 4, okay? But I'm not going to make a graph to see that. I'm just going to show you here the sort of the game we're going to play to actually evaluate this limit. And it is kind of a game. You have to sort of know the trick to pull here to evaluate this limit. So what we're going to do is we're going to go through a process that's called rationalizing here. In this case, we're going to rationalize the numerator. And rationalizing means I want to get rid of this square root, okay, from the numerator, okay. And you'll see why that, how that pays off in just a moment here when we actually go through the process. So that may be something that, you know, is not maybe something. I think that's something that's not completely obvious at all, right? That rationalizing the numerator here is going to allow you to evaluate the limit, right? Why would we expect you know, that to, you know, if we rationalize the numerator, why would we expect at all that allows us to evaluate the limit? So this is a kind of example that you need to have seen so that you would know in the future, oh, okay, if I have a problem like this one, if I have an expression like this one and I'm trying to evaluate the limit, it may benefit me to try rationalizing either the numerator or perhaps the denominator if the denominator had a square root in it. All right, now how do I actually rationalize this numerator? How do I get rid of this square root? Okay, well, what we're going to do is we're going to multiply here top and bottom. We have to multiply top and bottom because we don't want to change the expression. We don't want to change the value of the expression. We just want to make it look different. So I'm going to end up multiplying by what's called the conjugate of the numerator. See, this numerator is two terms, right? One of them is this square root and the second term is 3. And we're subtracting these two terms. So what I'm going to do is multiply by the sum instead of the difference of these two terms. I'm going to multiply by the sum of these two terms. Okay, that process shows up, or products like this show up frequently in mathematics. Okay, when you're factoring difference of two squares, that same if you recall your factoring patterns from way back in beginning algebra, if you're factoring a difference of two squares, that idea of multiplying a difference times a sum shows up there also. Okay. All right, so let me show you what happens here. So I'm going to multiply top and bottom here by, again, what's called the conjugate of, you don't need to know this term, but that's the technical term for it. What's called the conjugate of square root of x plus 5 minus 3. So I'm going to apply top and bottom by square root of x plus 5 plus 3, right? Now, again, I have to do it in the top and the bottom, right? Because if you take this quotient divided by this number divided by itself, that's 1. So you're really just multiplying this fraction by the number 1, but you're multiplying it by the number 1 in kind of an exotic form, right? Okay, so I multiply top and bottom by square root of x plus 5 plus 3, right? Now, what happens in the top is something really nice. So all I did was just wrote out the product. I'm multiplying the two things in the, right, the two factors in the numerator, and I'm multiplying also these two factors in the denominator. Now, I'm going to leave the denominator written in factored form, so I'm not actually ever going to multiply together. I'm not actually ever going to expand this product, x minus 4 times square root of x plus 5 plus 3. I'm going to leave that just written in factored form in the bottom. But in the top, I am going to expand the product. So I'm going to take square root of x plus 5 times square root of x plus 5. So I've done that here. And then square root of x plus 5 times 3. So that's 3 square root of x plus 5, right? And then minus 3 times square root of x plus 5. So there it is, minus 3 times square root of x plus 5. And then minus 3 times plus 3, of course, that's easy. That's minus 9. Now, you see what nice thing happens here? Because you're multiplying these conjugates together. Notice these two terms will disappear, right? Because they're opposite signs of one another. So you can scratch these out. Yay. And of course, the 9 is going to hang around. But notice here also you're multiplying square root of x plus 5 times the square root of x plus 5. Well, when you multiply a square root times itself, all you're going to do is just eliminate the square root, right? That would be like square root of 2 times square root of 2 is 2. Well, square root of x plus 5 times square root of x plus 5 just gives me x plus 5. So look what's happened. In the numerator, all the square roots have disappeared. So you don't have any more square roots. That's why I said I'm going to rationalize the numerator. Rationalizing means I'm going to get rid of the square roots out of the numerator. So now I end up with a nice numerator here. x plus 5 minus 9 is just x minus 4. Now, unfortunately, I didn't end up with a nice denominator, so that's why I left it in factored form. I didn't actually multiply these things out together. The numerator doesn't come out looking that nice. It still has a square root in it, right? So I've kind of just moved the square root from the numerator down to the denominator. But it turns out in this case, that's all right, because look what's going to happen. You're left with x minus 4 in the top, and now you also have a factor of x minus 4 in the bottom. So by kind of luck here, these are going to cancel each other out. So we got really lucky, and we ended up with 1 over square root of x plus 5 plus 3. So notice we didn't entirely get rid of the square root. It's still hanging around, but it's not in the numerator anymore. Now it's moved to the denominator. And even better, look, now you can evaluate this limit just by substituting. Oops, I pointed to the wrong place. But now you can evaluate this limit just by substituting 4 for x, right? Because when you substitute 4 for x, you get 1 over square root of 4 plus 5 plus 3. But let's see, 4 plus 5 is 9, and the square root of 9 is 3. So you get 1 over 3 plus 3. See, this is not 1 over 0. This is 1 over 6. So there's your limit. It turns out to be 1/6. So you actually do have a limit here, 1/6. So I claim that, if we plug values in for x that are closer and closer to 4 into this expression and simplify, we're going to come out with numbers closer and closer to 1/6. If you don't believe that, you can try it. Just plug in numbers that are not exactly equal to 4, right? Because that's going to give you a division by 0. But if you plug in numbers close to 4 and evaluate this expression, you get numbers close to 1/6. So the limit there is 1/6. So you see that little game there. You have to multiply the top and the bottom by the conjugate of the numerator, and things just turn out simplifying beautifully, and it turns out you can evaluate that limit. So if you have a problem like this in your homework, if you see a limit and it kind of resembles this example, going to have a quotient here and you're going to have a square root in it, you might try this. Looking at this example in the notes may give you a clue as to how to evaluate that limit. That's a pretty tough one. Okay, so as far as limits go, that one's pretty complex, right? Because it involves this, involves a special trick that, who's going to think of that unless you'd seen it before. Here's one that's a little bit easier now. So this one still takes a little bit of thought, though. So you cannot. So we're trying to figure out what's the limit as x approaches 0 of tan x over x. So here we have a trig function involved, right? So that, of course, makes things tougher automatically. And again, you cannot evaluate this one just by substituting 0 for x, which is very tempting to do. Of course, you can compute tangent of 0. That's easy. Tangent of 0 is 0, if you recall from trigonometry. So that's easy. But unfortunately, of course, when you substitute 0 for x, you get 0 in the denominator. So here we're back with dividing by 0, okay? And so that causes us issues. So that could mean that this limit does not exist, okay? Or it may be that the limit is infinity, right? Which is almost as bad as not existing. All right, so so that indeed could be the case. Maybe this is just not a reasonable question, right? Maybe this limit doesn't exist, but maybe it does. So so you do have to be a little bit careful. And actually, in this case, it turns out the limit does exist. So it turns out that as x approaches 0, if you plug in smaller and smaller values for x, values that are getting closer and closer to 0, and evaluate tangent of x over x, it wounds up that you end up with a limit of 1. So it turns out that these values get closer and closer to 1. So there really is a limit here. So if you graph this function, tangent of x divided by x, and look at what happens close to 0, you'll see that curve is getting closer to 1 on the y-axis. All right, now let me show you how you can discover that, though, without actually making the graph. So, you know, it involves something that we often do, right, in trigonometry. Let's take tangent and let's convert it back into its primitive form, which is sine of x divided by cosine of x, right? So we know that tangent of x is sine divided by cosine, right? So I'm going to rewrite that tangent as sine of x over cosine of x. And then I'm going to think about sine of x divided by cosine of x, all of that divided by x. What does that really mean? Well, remember, when you divide by a number, that's the same as multiplying by the reciprocal. So we're taking sine x over cosine of x, we're dividing it by x. So that's the same as taking sine x over cosine of x and multiplying it by 1 over x, right? Dividing by x is the same as multiplying by 1 over x. So I'm going to write this complex fraction where you have, you know, where you have a fraction inside of a larger fraction. I'm going to write that as this product, sine x over cosine x times 1 over x. Multiplying by 1 over x is the same as dividing by x, right? And the reason that's helpful now is I'm going to break up this product in a little bit unusual way. So I'm going to write this as sine x over x. So I'm going to put these two things together, sine x over x, and then I'm going to put the 1 over cosine x separately. So this product is the same as this one. I've just kind of rearranged the factors, right? I switched the cosine of x and the x, right, in the bottom. So I get the limit as x approaches 0 of sine x over x times 1 over cosine x. Now, you remember, this still looks like it's a problem, right? Because as x approaches 0, 0 still looks here like you're dividing by 0, right? But remember, we already learned, right, that right at the beginning when we were talking about limits, it turns out that the limit as x approaches 0 of sine x over x, that is a special limit. That goes to 1, okay? So there's something you have to recall. The limit as x approaches 0 of sine x over x, that approaches 1. We saw that from looking at the graph of sine x over x. So, so that limit you just have to sort of be aware of, right? The limit as x approaches 0 of sine x over x, that is 1. Now, this limit is easy because you can evaluate this second factor is easy to determine its limit, because that you can figure out just by plugging 0 in for x. Because what's the cosine of 0, someone? What's cosine of 0? Someone recall that?
0?
No, what's cosine of 0? When you evaluate cosine of 0 on your calculator, what does it tell you that it is? What now? 1, right? So yeah, so you can figure out this limit, the limit as x approaches 0 of 1 over cosine of x. You can do that easily just by plugging 0 in for x, and you get 1 over 1. Because cosine of 0 is 1. So remember, this limit we just learned, so that's something you just have to know. This limit as x approaches 0 of sine x over x is 1. And then this one is easy to determine, is 1 divided by 1. So you get 1 times 1 over 1, which of course, that's a bunch of 1s. So that ends up being just 1. So indeed, this limit does exist, and it's 1. So if you graph a tangent of x divided by x, as I mentioned a moment ago, and look at what happens as x approaches 0, it turns out that graph is moving toward 1 on the y-axis. Okay, so this is something that you just have to recall, that limit of sine x over x as x approaches 0, that's 1. And we found that at the hard way just by experimenting with this, limit back in the previous notes. All right, let's see what happens on this one now. This looks like sine x over x, right? So this looks like the limit as x approaches 0 of sine x over x, which of course, you know that's 1. So it looks like this limit should be something like 1. However, this is not sine x over x. This is sine of 4x over x. So that's a little bit different because you have a 4x here and you don't have a 4x here. So, so that makes it something a little bit different, right? So we can't automatically think, oh, this limit is going to be 1. This is not quite sine x over x as x approaches 0. This is sine of 4x over x as x approaches 0. All right, let me show you how we can fix this, though. So we actually are going to make this look like sine x over x. Let me show you how. So I'm going to multiply here. So I'm going to play a little game again. All right, so this is another little trick that you need to have seen. Okay, you need to have someone show you so that you'll see how this works. So I'm going to multiply top and bottom of this fraction by 4. Of course, 4 over 4 is 1. So you're really not changing this fraction at all. We're just going to make it look slightly different, right? Okay. So I'm going to multiply 4 into the denominator here, and I'm also, thinking of multiplying 4 into the numerator as well. But when I do that multiplication, I'm actually going to move the 4 into the denominator. So I'm going to write 4x in the denominator, but I'm going to keep this 4. I'm going to keep this 4 in front. So I'm not actually going to combine. I'm not actually going to write that next to the sine 4x. So so this 4 I'm going to keep in front, and this 4 I'm going to put in the denominator. So I get 4 times sine of 4x over 4x. Now that is something more like sine x over x, right? It's sine of something divided by that same something. Okay, in this case, that something is 4x. So I made this look closer to a limit that I know the value for, right? But keep this 4 outside. Now, just to make this look correct, I'm going to do a substitution here. So let's let y be equal to 4x. So I'm going to make this substitution. I'm going to say y is 4x. And then instead of writing a 4x in the top and the bottom, I'm going to write y. Okay. So I'm going to write this as sine y divided by y. Now, if x is going to 0, right? If x is going to 0, then 4 times x is also going to 0, right? Okay. If you take 4 times a smaller and smaller number, then 4 times the smaller and smaller number is still a smaller and smaller number, right? So if x is going to 0, notice that y is also going to 0. So I can change this limit to the limit as y approaches 0 of 4 times sine y over y. But now you know what this limit is going to be, right? This is like the limit as x approaches 0 of sine x over x. So this limit I know is going to be just 1. This 4 is still here, though. So you end up with 4 times 1 as your limit value, which is 4. So, so this limit turns out to be not quite 1, but instead 4. We might have actually deduced that already right here without making this substitution. I think it would be fair, actually, to stop right here and say, okay, here I have sine of a quantity divided by a quantity, that same quantity. That quantity is going to 0. So what's that limit going to be? Oh, that limit's going to be 1, right? So you sort of, at this point, you can already figure out, oh, this limit's going to be 1. So you have 4 times 1, which is 4. So the limit there has to turn out to be 4. I know in the homework now, there's a couple of them that are kind of similar to this one. So keep this example in mind when you're looking at those couple of problems from the homeworks. All right, we got one last example to look at, okay, of limits. And this one turns out to be kind of trivial, all right? So yeah, this is not sine x over x, this is cosine x over x. What's the difference going to be? Here we're letting x go to 0 again. But look, this one doesn't require much thought, okay? Because as x goes to 0, cosine x is going to be getting closer to what? What's cosine of 0? Did we just mention that a moment ago?
1.
1, right. So as x goes to 0, notice the top here is getting closer to 1, right? Okay, so the top is getting close to 1. But as x goes to 0, the bottom, unfortunately, of course, is going to 0. So you end up with sort of this quantity, right? Okay, which is undefined. 1 over 0 is undefined. But think about what's happening here. The numerator is getting close to 0. I'm sorry, the numerator is getting close to 1, but the denominator there is getting smaller and smaller, getting closer and closer to 0. So, so what's going to happen to this? When you do this arithmetic, what's going to happen to this quotient? So you're dividing a number that's close to 1 by a number that's very close to 0. When you divide 1 by a little tiny number, or a number that's getting smaller and smaller, what's going to happen to that? What's going to happen to that fraction? What happens when you divide numerators by really tiny numbers? What happens to the quotient?
It's undefined.
Well, yeah, it's undefined kind of, but let's be a little bit more specific. So let's just mentally think of this. I'm going to write it down, but you can think of this in your mind. So you have a number that's very close to 1, but you're dividing it by something really small. So let's plug in some really small values here. For instance, what's 1 divided by 0.01? What's 1 divided by 1/100? What does that equal to?
You get like a big number.
Yeah, you start getting really big numbers, right? Okay, so 1 divided by 0.01 is 100, or 1 divided by 0.001, that's 1,000, right? Okay, or 1 divided by 0.0001, that's 10,000, right? So in this fraction, as x gets smaller and smaller, since the numerator is getting close to 1, right? Since the numerator is getting close to 1, but the denominator is getting very, very tiny, what's going to happen is this fraction is going to start blowing up, right? It's going to get really large. Now, it might be positive infinity, or it could be negative infinity, right? Because, you can choose the x value to be negative. It could be minus 0.01 or minus 0.001 or minus 0.0001, right? Okay. But it's either going to be plus or minus infinity, right? Okay. And so, see, this limit doesn't exist, right? This limit is undefined because these fractions are getting, going to be getting really, really big, right? You're going to start either a really big positive number or a really, really small negative number if you choose a negative value for x. So, so you can deduce that, yeah, this limit doesn't exist, right? Okay, because these values are going to be getting really large or really small. So when you graph this function, when you graph this function, you can figure out what's going to happen to the graph, right? When you graph this function close to 0, close to x equals 0, what's happening to the curve? Right there close to x equals 0, man. It's doing.
Do we have like an asymptote or something?
Yeah, well, yeah, you have an asymptote, right? So I think on the right hand side, the curve is going to start shooting up to positive infinity. Okay, because these numbers are going to be getting really, really large. See, like I've got here 0.1, 0.01, 0.001. See what's happening to the y values? They're getting really, really large, right? On this side, though, I think you'll get just the opposite. You'll get small negative numbers. So the graph will start falling off like this on that side. But in either case, so in either case, right, you're not going to have a limit, right? So this limit really doesn't exist. It's undefined. Okay. So that's a situation to be careful of when you're evaluating limits, because this frequently happens. If your numerator is moving to some fixed number, okay, like 1, or it could be any fixed number, right? But if the denominator is getting very, very tiny, very, very close to 0, that means you're going to end up with really big or really small quotients, and so the limit's not going to exist. Okay. That means in your graph, you're going to have a picture like this one. You're going to have an asymptote, as you said, Colin. Okay, so that's not like sine x over x. That really gets close to 1, but cosine x over x just explodes to positive or negative infinity. Okay, gets far, far away from 1, in fact. All right, so so there's a few more examples of evaluating. There's a few more examples of evaluating limits. Okay. All right, let's do something now that's a little bit more, maybe a little bit more concrete. All right, and so we're going to talk about, as I mentioned, finding local minima and local maxima. And so now sort of the definition of a local minimum and a local maximum. So here's a graph of a function, right? Okay, so I just made this one up. So nice function here, and it's got some turning points, right? And so those peak turning points, remember, we refer to those as local maxima. So here's an example of a local maximum, this turning point, and that peak turning point, and this valley turning point would be an example of a local, what's called a local minimum. The reason we use the term local, why do we throw the word local in there, that adjective local in, is because close to this point, right? Okay. Near this point, that is the minimum, I'm sorry, that is the maximum of this function, right? When you're close to this point, or when you're close to this point, that's the minimum from the function. So locally, close to this point, this is a minimum for the function, right? Or close to this point locally, this is a maximum for the function. Here's another a local maximum over here on the right hand side. So you can have more than one local maximum, right? And you can have more than one local minimum. Now, if you have a minimum or a maximum that turns out to be the maximum altogether of the function, or if you have a minimum that's the minimum altogether of the function, that's called an absolute maximum or an absolute minimum. So this point is an example on this graph of an absolute maximum, because this graph never goes above this turning point, right? Anywhere. But this minimum is not an absolute minimum. Okay, it's a local minimum, but it's not an absolute minimum, because eventually on the left and the right, notice this graph dips below this point. Okay, so this is a local minimum, but it's not an absolute minimum, because over here on the far right, the graph eventually does drop below this minimum value, right? Or over here on the far left also, the graph drops below this minimum value. Now, as I mentioned right at the beginning of the course, right, when you use the term local minimum or local maximum, that actually refers to the y coordinate of the point. Okay, so technically the local minimum here is 2, all right, and it occurs at x equals 1. the local maximum here is 4, and it occurs at x equals -2. Here, the absolute maximum is 8, and it occurs at x equals 5. But we're very loose with the terminology. So so often we'll refer to the whole point as the local minimum, or the whole point as the local maximum, although technically that's not quite correct. All right. So do you understand the difference between absolute and local? Right. Okay. So this is a local maximum because near this point in this locale, right, in this location, indeed, this is the maximum point. But it's not the absolute maximum because over here to the right, eventually the graph goes above this point, right? But this is the absolute maximum because the graph never, ever goes above this point, right? This is a local minimum, but it's not an absolute minimum because eventually on the left and the right, the graph dips below this point. Okay, now, the key fact that you already know, and so we can restate it, but you're already familiar with this fact, is, well, I'm a little bit ahead of myself here. Okay, it's what's called the relative extrema theorem. All right, but before I state the relative extrema theorem, I have to make another definition. Okay, so we have to define what's called a critical number. So that's an easy definition. A critical number is any x value where the derivative is 0 or where the derivative is undefined. So if you have an x value where the derivative is 0, or there's a second possibility, and this one's easier to overlook. If you have an x value where the derivative is undefined, so if you have an x value that's not in the domain of your derivative, then such an x value is called a critical number. So if you look at this, function, this kind of goofy looking function here, okay, it has 3 critical values, all right, because there are going to be 3 places where the derivative is 0 or undefined, okay. The number 2 is the obvious one to look at there. So right there, you have, if you draw the tangent line right here, correct, you're going to get a horizontal tangent line. And so that means the derivative is going to be 0, right? So this is an example of 2 is an example of a critical number for this function because f prime of 2 is 0, okay? So again, if you have a number where the derivative is 0, where the tangent line is horizontal, such a number is called a critical value for the function. Now, these 2 points also are critical values of this function. So, gosh, what numbers are those? I picked those are bad numbers. I can't tell what they are. All right. This looks like it's about, well, I don't know. Let me not try to guess what that number is. So let me call this C sub 1. I don't know what that number is. And let me call this C sub 2. So you have 2 other critical numbers for this. You have 2 other critical numbers for this function. All right. Whatever this x value is, it's somewhere between -1 and -2, right? And whatever this x value is, that also is a critical number, somewhere between 5 and 6. If you plug either one of these numbers into the derivative, what are you going to get? So if you plug C1 into the derivative, not the original function, but into the derivative of this function, what do you get? Colin, do you have a guess there? So if I plug this into
I don't like it.
What now?
They don't look right. They look like
yeah, we talked about this, but it was a long time ago. What happens at sharp corner points on graphs? What happens to the derivative there?
Isn't it undefined or
It's undefined? Yeah, that's right. remember way back several weeks ago when we were first talking about derivatives, I think it was even before the first test, we mentioned that at sharp turning points, you don't have a derivative. Okay, so at this value C1, whatever that is, the derivative is going to be undefined. And same thing here, because you've got a sharp corner point here. Also, so f of C2 also is going to be undefined. But that makes it a critical number, all right? Because critical numbers are going to be where the derivative is 0, like here at 2, or where the derivative is undefined, okay? So, so this function has 3 critical numbers. This one, and this one. Maybe I should circle them down here. That's a critical number, that's a critical number, and that also is a critical number, okay? Remember, the critical number is the x value, right? A critical number is not a point, it's just a single number, right? Now, what's important about critical numbers is what you could already guess, right? It's going to be critical numbers where you have a turning point, okay? So you can only have turning points on functions. So that would be a relative maximum or a relative minimum. You can only have those at critical numbers, right?
Oh, pause. Question.
Yes.
What about those things where they change the rate? That's like an inflection point or something. Does that count as a critical one, or
no?
It's not.
But that's a good question. Okay, so let me draw a. Just because you have a wiggle in a graph doesn't make it a critical number. So if you had a graph like this one, okay, right there you have kind of a wiggle in the graph, right? And so that's an important point on the graph, because that's where the concavity is changing. Notice this side column is what? Concave down, and this side is concave up. So that's an inflection point, but that whatever that x value is there, that's not a critical number. Okay, all right. Not going to be a whatever this x value is down here. That won't be a critical number. All right. And notice that that conforms to this theorem, because at critical numbers, what can happen? You can have turning points, right? Okay. But you don't have a turning point right here. You have an inflection point, but it's not a turning point. So, but your point is well taken. You're going to see that you're going to see a little bit later that actually inflection points kind of are very similar to turning points. Okay, so I'm making this distinction here, but it's really not as clear as I'm trying to imply that it is. Okay, but for right now we're only working with. For right now, we're only working with first derivatives, though. What?
I just wanted to watch out for trick questions, because
yeah, well, okay, right. So, yeah, I love trick questions, but and we may have an opportunity, but not yet. All right, so so let's start with some problems now that you have already done. So you know how to do these problems now already. So they're going to be very familiar to you. Maybe the algebra is difficult, but the nature of the problem is really going to be straightforward. But I want to remind you of this theorem, right? This is a really important theorem, but again, it's already kind of familiar to us. If you're going to have a relative maximum or a relative minimum, that is, if you're going to have a turning point, the only place you can get that is a critical number. So you cannot have turning points away from critical numbers. So what that means is that if you're looking for turning points, what you're really looking for are critical numbers, okay, right? So that's really the secret for finding turning points, is to find the critical numbers. All right, so so let's take a look at some examples now, okay? So this says find the possible extrema. Notice it says possible extrema So we're not really actually looking for the actual extreme values. That is the relative maximum values and the relative minimum values. When you collapse those together, those are called extreme values. So, and the plural of extreme values is extrema. So this could be a local minimum. So when I say extrema here, that could be a local minimum or a local maximum, one or the other. So we're looking for, in other words, we're looking for possible turning points here. But notice it just says possible turning points. We don't have to confirm that we've got actual turning points. I guess we can look at the graph and confirm that, right? Okay, but here we're just looking for possibilities of this particular function. So 3x to the fourth minus 4x cubed. So that's a polynomial function because it just has a whole number of powers of x in it, this is a fourth degree polynomial function because you've got x to the fourth power here. All right, so so the extreme value theorem tells us what are we really looking for here? We're really looking for critical numbers, right? And how do we find critical numbers? What are critical numbers? They're going to be where what is the case?
Turning points.
What? Well, that's where you have possible turning points, right? Okay, but what's the definition of a critical number? Either what? The derivative is what? I'm pointing at it there.
The derivative is 0.
Or the derivative is what?
Undefined.
Undefined, right. So you're looking at where the derivative is 0 or where, and that second possibility is often overlooked, but it's important, where the derivative is undefined. See, because on this graph, you have these two turning points, but the derivative is undefined there, right? Okay. So, so you have to look at that second possibility. All right, so basically we're just taking the derivative and we're setting it to 0, correct? I mean, that's, so how many times have we done that? Like dozens of times already. So we're just, you know, sort of relearning something that we already know how to do, right? Or we're just kind of reviewing something they already know how to do. So, well, y'all should be really good now at calculating derivatives. Actually, you're quite expert at this now. So what is the derivative here? Can y'all just rip that one off really fast there? Okay, so yeah, all right. So I see 12x cubed is first term, right? Because you bring the 4 down. And then what's the second term in the derivative? Bring the 3 down. So you would get what? 3 times the 4 is 12x squared, right? So, oh, we get kind of a nice looking derivative there, just 12x cubed minus 12x squared. And we're going to do something with that, right? Because we're trying to figure out where that's 0. So we just set that to 0. And now we have an equation to solve, okay? Well, I don't think this one's too hard to solve. I can solve this one by factoring. So I can factor out a 12 and an x squared. So I get 12x squared times x minus 1 is equal to 0. So see, I can solve this equation by factoring. So this means either 12x squared is equal to 0 or x minus 1 is equal to 0. So don't forget, you know, you can solve equations, especially equations with higher powers of x in them, right? You can solve those by factoring often. Sometimes you can't solve them by factoring, but often you can solve them by factoring. And here you can solve this one by factoring. Let's see, if 12x squared is equal to 0, I think that means x just, there's really only one possibility for x, right? X has to be what, 0, right? Yeah, I mean, 12 times x squared is 0. That means x just got to be 0. And here, if x minus 1 is 0, that means x just has to be 1. So there are your two critical numbers, 0 and 1. So if we're going to have a turning point, got to be at 0 or 1. Oops, there's one other possibility. Don't forget, we also need to look for where the first derivative is undefined. So is there any x value we cannot plug into this formula? I don't think so. I think if you plug in any x into this formula, you can do the arithmetic, right? You can cube any x number, you can square any x number, you can multiply by 12 and subtract. So, so I think the derivative here is defined everywhere. So for any x value. So not going to worry about the derivative being undefined. So that's it. There are your only two critical numbers, x equals 0 and x equal 1. If you plug those back into the original function, then what are our two possible extreme points? Well, if you plug 0 in for x, here you're going to get what? Y equals 0 also. So there's one of your possible turning points at 0, 0. And if you plug 1 in for x, make sure you go back to the original function now. If you plug 1 in for x, I think you get 3 times 1 minus 4 times 1. You'll get minus 1 there. So there's your other possible turning point. I keep stressing possible because maybe these aren't really turning points. So if we graph the function, it may turn out just by bad luck, it may turn out that these are not really turning points. Well, let's actually graph this one and see. I think I have a graph here of this one. Oh, I do. So yeah, so there's the graph. And do we have turning points? What I said was correct. Look what's happening at 0, 0. That is not a turning point. Wow. Okay. So 0, 0 was a possible turning point, but it turned out to not be an actual turning point. See, here it's decreasing, and then you have a wiggle here, right? Okay, but it continues to decrease. So this is not really a turning point. But we do have a turning point at 1 and -1. Okay. So Colin, there's exactly what I was talking about a moment ago. See, you have a wiggle here in the graph, but you don't actually end up with a turning point there at 0, 0. So that was a possible turning point, but turned out to not be an authentic turning point when we look at the graph. However, Colin, this is what sort of point? It is an important point. What sort of point is this one? We only have really
inflection.
Yeah, that's an inflection point, right? Because notice the concavity is switching from concave up. This part is concave up because it's bent up, right? But this part is concave down. Right here is concave down, so just slightly concave down. So you do have an inflection point at 0, 0. You're going to have another inflection point over here somewhere. I'm not exactly sure where it is, because this part of the curve is concave up again. So somewhere right around there is a second inflection point. So that's interesting. We have two inflection points here. But we haven't talked about how to locate inflection points yet, right? Okay. So we have to save that. But we do now locate possible turning points, and it turns out that only one of our possible turning points is really an authentic turning point. Okay. All right. Well, we want to try some other examples, right? But that's a very basic example. So if you can understand that example, you kind of really have it. All right. Except for maybe some algebra problems, because when you're looking for critical values, you have to solve equations, and okay, so that involves algebra, and that always can be difficult. But if you understand the process here, then that's 75% of the battle, I think. So remember, when you're looking for possible extrema, what you're really looking for are critical numbers, and critical numbers are where the derivative is 0, or possibly where the derivative is undefined, but that didn't happen in this particular problem. All right, well, let's take a look at, we want to look at some other examples too. So here's another example. We want to find the possible extrema of this function. Let me show you a graph of this one. See if I can find it. I think it's this one. Yeah, that's it, right? So, oh, cool. So, so indeed, I think we clearly have some turning points here, right? We've got a turning point right there, but notice that's an unusual turning point. That's a sharp turning point, but that nevertheless is a turning point. So we have a turning point at 0, 0. So we want to see if we can find that one. And we have another turning point at, I'm kind of hung up on 1, -1 as a turning point, because that also has a turning point. It looks like 1 - 1 right there, okay, is a second turning point. By the way, notice this turning point is not an inflection point, not an inflection point. This part of the curve is concave up very slightly, but there's a little bit of curvature here, but it's concave up. This is also concave up though. So it doesn't switch concavity at 0, 0. So don't have an inflection point here. Well, we don't care anyway, because we're not looking for inflection points yet, but I did want to point out that that's not an inflection point. But it is certainly a turning point. It's a sharp turning point, but that still counts as a turning point. So, so we can tell by looking at the graph that we should be able to find some possible turning points here, 2 of them. So we're going to see if we can find those. All right, but let's take a break first before we launch into the algebra here. This does involve a little bit of algebra. So let's come back at about 12:40, okay, and we'll go through the process here. All right. Okay. So I'll see y'all in a few minutes if I can see if I can stop the. Hey, we're back. So let's resume here. So I hope everyone is back and paying attention again. Let's see what's going on in this problem, because we already saw that there were a couple of turning points, right? So, but one of them was a sharp turning point. So let's see how that comes about from examining the first derivative. So again, you're going to have to compute your derivative here, right? First, and then set that to 0, and solve an equation. But you also want to be paying attention to if it's the case where the first derivative is not defined, right? I should say, actually, we're looking for when we're looking for critical values where the first derivative is not defined. I got to be careful. You have to have a number where the first derivative is not defined, but it's in the domain of the original function. So if you have a number that's completely outside of the domain of the original function, obviously you can't have a turning point there, right? Okay, because the graph won't exist at numbers that are outside of the domain of the function. So, so you'd be looking for critical numbers. Again, it can be where the first derivative is 0, or where the first derivative is undefined, but the number is in the domain of the function. So I don't think I made that distinction earlier, but that's kind of important to remember. All right, let's take the derivative here, though. And
I have a question. Quickly.
Yes.
Sorry. What about a imaginary number?
No, we won't. In this course, we won't. We're only dealing with real valued functions, so we won't worry about imaginary numbers. Okay. But in situations where you're dealing with functions where the output can be a complex number or an imaginary number, then yeah, you might have to take into account imaginary values. Okay, so let's see what the derivative is here. So for the first term, that's easy. The derivative is going to be 2, because that term is just 2 times x, right? And now for the second term, well, you're going to bring the 2/3 down, right? And multiply by the 3. And then you'll have x to the, and now here's where you have to be a little bit careful, right? It's going to be 2/3 minus 1, which is going to give you minus 1/3. So you have 2, and then here the 3's will divide out. So you'll have 2 minus 2 times x to the minus 1/3 power. And then that would be 2 minus 2 over x to the positive 1/3 power. And if you want to, you could write that 1/3 power means cube root. So if you wanted to, you could write this as the as the cube root of x. Actually, let me do it like that, because that may be more convenient in just a moment here. Okay, so all right, so there's our derivative, and the first thing you can see here is that the derivative, when you plug 0 in for the derivative, you're going to end up with undefined, okay? Because because you're going to try to compute 2 minus 2 over the cube root of 0, and the cube root of 0 is 0. So you end up with 2 divided by 0, and that is undefined. So it looks like we're going to have a 0 is going to be a critical number. Or we may have a possible turning point at x equals 0. And if you plug 0 into the original formula for x, you get 2 times 0 minus 3 times 0 to the 2/3 power. But 0 to the 2/3 power is 0. So you end up with 0 there as your matching y values. So here's a possible turning point at 0, 0. And we already noticed that that actually did turn out to be a turning point, right? Okay. It turned out to be a sharp turning point. Okay. And the clue that that was going to be a sharp turning point here, right, is that you don't have a derivative, right? Remember, you don't have derivatives at sharp turning points. And indeed, at x equals 0, the derivative is undefined. Okay, so there's one of our possible turning points. And now the other turning point we would get by taking the derivative and setting it to 0, and then try to solve this equation. So let's see if we can solve this equation. 2 minus 2 over the cube root of x equals 0. Well, I really don't like having fractions, especially a fraction with a cube root in it. So I'm going to try to get the fraction out of this equation. And you can do that pretty easily by multiplying both sides of the equation by cube root of x. So I'm going to multiply both sides here by cube root of x. And so what do we get? Well, on the right-hand side, you get 0, because 0 times the cube root of x is 0. So that's easy. And on the left-hand side, you get, well, 2 times the cube root of x is, well, that's 2 times the cube root of x, right? And then when you multiply the cube root into the second term, well, the cube roots divide out. And so you get minus 2. Cube root here times this cube root that will divide out, and so you just get a minus 2. Well, that equation is looking easier to solve. I'll bring the 2 over to the right-hand side. So I have 2 times the cube root of x is equal to 2, positive 2. And now you can divide both sides by 2. So that will make it even easier. So I'll have cube root of x is equal to 1. And that you can solve just by inspection, because what number has cube root 1? What has x got to be here? There's only one number whose cube root is 1, right? What's x got to be? Sure, it's 1, right? X just has to be 1. Another way you can think of that is cube both sides. So you can think of cubing both sides of the equation. When you cube a cube root, the cube root goes away, so you'll just get x, and of course 1 cubed is 1. So there's your other possible turning point. It's going to occur when x is equal to 1. So now let's see what happens when x is equal to 1 right here. So let's try computing g of 1. So that would be 2 times 1 minus 3 times 1 to the 2/3 power. Now, normally computing a 2/3 power would be a little bit difficult, but in this case not, because when you take 1 to any power, that just gives you 1. So 1 raised to any power is just going to be 1. And so you just end up here with 2 minus 3 here, which is minus 1. So there's the other possible turning point at 1 and -1. And we already saw the graph, right? So we know that, yeah, this really is a turning point. It's not just a possible turning point. There's a sharp turning point right there at 0, 0. And there's also a much smoother turning point right here at 1, -1. This one is a local maximum, and this one is a local minimum. Really can't see that yet without looking at the graph, right? Okay, but we already saw the graph, so we knew which one was a local maximum and which one was a local minimum. Okay, here's one now that's a little bit harder. So this one, because it involves some trig functions. So we want to find the possible turning points, right, of 2x minus cosine of 2x. But now, since this formula involves trig functions, you know, when you graph this curve, it's probably going to be periodic, right? So you're probably going to have a lot of waves in this curve, okay? So because it involves sine and cosine, right? And sine and cosine, their graphs, you know, are very wavy, correct? And so that means that you probably have lots of turning points, probably. And so so we have to limit ourselves to just finding the turning points from 0 to 2 pi, because I think if we were looking for all the turning points, there's probably going to be infinitely many of them. Actually, let's take a look at a graph of this one, and you'll get this really is a cool graph when you graph this one, and it does have lots of turning points on it. So there's the graph, and this is, I just drew the part from this is 0 and 2 pi is, you know, about 6.28. So I cut off here roughly at about 2 pi on the right hand side. So see, there's a bunch of we got a bunch of waves in this graph, and so we've got lots of turning points here, right? In fact, 1, 2, 3, 4, right? Just from 0 to 2 pi. Wow. So lots of turning points there that we were looking for. If we extend this graph, oh, you can see, right? It's periodic, right? So as you go from left to right, it just keeps repeating itself. So you know, you've got a ton of turning points. Infinitely many turning points on this function, so you can't find all of them, right? So so we're just limiting ourselves to turning points here between 0 and 2 pi. Okay. All right. So so if we weren't looking at the graph, and if we weren't cheating by looking at the graph, how could we find those? How could we find those possible turning points? Right. Well, it's always the same process, right? You want to find where the derivative is 0 or where the derivative is undefined. So let's see if we can calculate the derivative here, right? So y'all should be able to calculate this derivative. This is something that you could have done on the test really easily. What's the derivative of 2 sine of x? Someone, Van, what's the derivative of 2 sine of x? I know you know that.
2 cosine x.
What now?
2 cosine x.
Yeah, 2 cosine x, right? So that's so easy. And so that's easy, Van. And what about the derivative of cosine of 2x, right? So have to be a little bit careful there. What, Van?
Negative sine of 2x times 2.
Right. Minus sine of 2x. But then Van said it perfectly there. You have to remember that this is not just x, this is 2x. So you have to finish this derivative by multiplying in the derivative of 2x, which is 2, right? So let's put that in front. So I have to multiply in a 2 as well, right? As part of that derivative. So so this is nice. We get 2 cosine of x plus 2 sine of 2x. And now let's see, we want to do what with that? So Van, to put the regular numbers, what do we do? Or Alva, what do we do?
Simplify the 2 out.
Well, yeah, as the process of, in the process of doing what?
Of finding the derivative.
Well, we
No.
found the derivative. So there's the derivative, right? But what do we do with the derivative now to find the critical numbers? The critical numbers are going to be where the derivative is what? Equal to what?
0.
0, right? So set this to 0. Okay. It's also where the where the derivative is undefined, but here trig functions, their domain is all real numbers. So this derivative is not gonna be undefined anywhere. Okay, you can plug any x value into this derivative and do the calculations here. You might have to have your calculator help you, right? Computing the sine and the cosine, but you'd be able to do that. Okay. All right. So, wow, we have to try to solve this. Darn it, we have to try to solve this equation. That looks kind of tough, right? Especially because this is cosine of x and this is sine of 2x. So it's unfortunately, we don't even have the same value there. Same expression inside the trig functions, right? This is just cosine of plane x, and this is sine of 2x, all right? But this is where some of your trig knowledge can really benefit you here, because do you recall there's a identity for sine of 2x? You remember there's a way for simplifying sine of 2x? Did y'all learn that when you were learning about trig? It's called the double angle identity. And I think it's sine of 2x turns out to be 2 sine of x cosine of x. Was someone getting ready to say that?
Yeah, I think that's correct.
You think that's correct? Yeah, that's what I was trying to recall. Right? Okay. Yeah. So from trig, there's a kind of a useful identity in trig that when you're taking sine of twice an angle, that turns out to be just 2 times sine of the angle cosine of the angle. So sine of 2x is 2 times the sine of x times the cosine of x. Okay, that's one of the trig identities that comes up actually kind of frequently. All right. Also, cosine of 2x comes up sometimes as well and is useful. All right, so I'm going to change the sine of 2x to 2 sine of x cosine of x. Of course, it's got to be multiplied by this 2 here, so that gives you 4. So you get 2 cosine of x plus 4 sine of x cosine of x. But now we're wondering, how are we going to solve this equation, right? Equals 0. But remember, one of our basic tricks for solving equations, right? One of our basic tricks for solving equations is always to factor. That is always a useful tool in solving equations. And you can factor this expression, right? Because notice in both of these terms here on the left-hand side, you have a cosine of x that you can factor out. Also, from the coefficients, you can factor out a 2. So let's factor that out. So I'm going to factor out 2 cosine x from both terms. So when you factor 2 cosine x out of the first term, well, that just gives you 1. But when you factor it from the second term, let's see, when you factor 2 from 4, you give 2. And then we factored out the cosine of x, right? So we're just left with sine of x. Wow. So look, what this is telling us is 2 cosine of x has got to be 0, or 1 plus 2 sine of x has to be 0. Because you see, you've got this product equals 0, and the only way that happens is if one of the factors is 0. Now, these equations, I think, are much easier for us to deal with. If you divide both sides here by 2, you get just cosine of x is equal to 0. And I bet y'all know where cosine of x is equal to 0. So what angles are going to give you cosine of x equal 0?
1.
No, cosine of 0 is 1 alpha, right? But what angle gives you cosine of 0? Let's
Pi
draw
over
a little, what now?
Pi over 2.
Ah, yes, pi over 2 is one of them, right? Y'all remember how cosine works, right? We draw a
And
little
then 3 pi over 2.
coordinate system, right? At 0, cosine is 1. But when you go up to pi over 2, cosine becomes 0, right? And then what about when you go over here to pi? What's cosine of pi? So it's 0, 1.
-1.
I'm sorry, it's 1, 0, and then -1. And then when you go to 3 pi over 2,
0 again.
0 again. And then when you come back up to 2 pi, it's back to 1, right? Because that's one full revolution. So cosine of 0 is 1, then cosine of pi over 2 is 0, then cosine of pi is -1, then cosine of 3 pi over 2 is 0, and then cosine of 2 pi is back to 1 again. So here, you know, oh, x has to be, there's two possibilities, minus pi over 2, I'm sorry, positive pi over 2, and then positive 3 pi over 2, right? Okay, at pi over 2 and at 3 pi over 2, cosine is 0. Oh, so there are two possible turning points. One of them is at x equal pi over 2, and one of them is at x equal 3 pi over 2. Does that what our graph shows? Let's look here if I can see what's on the graph. So we said, there's going to be a turning point at pi over 2. What is pi over 2? About 1.5 something? There it is. There's that turning point at a little bit more than 1.5, right? And how much is 3 pi over 2? Can y'all estimate that for me on a calculator? How much is 3 pi over 2 in numbers?
Is it 4.71239?
Wait, say that. What? Say that again, Colin. What?
4.7-ish?
4.7-ish, right there. Must be right there, right? Okay. So there indeed is another, that must be 3 pi over 2 right there, right? Okay. As another possible turning point. So there you see, we found a couple of turning points. Notice it's nice, we don't have to estimate them from looking at the graph, right? We know this number is really 3 pi over 2, right? Okay. And we know this number is right there is really pi over 2. All right. Oh, so we located two of the, it looks like there's two more though. I wonder what this one is. And I wonder what this one is, right? What in the world could those be? Okay. So, so we've still got two other turning points, all right, to locate there. That means there got to be two other critical values. All right. So let's see if we can find, those other two. They must come from the solutions of this equation, right? 1 plus 2 sine of x equals 0. I didn't fill in the y coordinate here, by the way. I didn't fill in the y coordinate for these points, but you can do that. Just take pi over 2, plug it back into your function, right? Take 3 pi over 2, plug that into your function, and you can get the y coordinates for those turning points. All right, let's see if we can locate those other two turning points. So they must come from the solutions of this equation. So let's see, I have 2 sine of x equals -1. I'm going to bring the -1 back over to the right. That looks like minus square root, but that's supposed to be -1. And of course, divide by 2. So I have, oops, now I have to think about this. Sine of x is -1/2. Wow, where is sine of x going to be -1/2? Oh boy, let's draw another set of axes here. And now I have to remember where is sine of x going to be minus 1/2. Now, so the negative is a little bit tricky there. So let's make that a little bit easier to start with here. So where is sine of x positive 1/2? So can you remember from your special angles? Where is sine of x positive 1/2? It's not at 0 because sine of 0 is 0.
30
Right.
degrees.
What now, Colin?
Sine of 30 degrees, but I don't remember radians.
Yeah, it's 30 degrees. That's right. It's pi over 6, right? Okay. So sine of pi over 6 is positive 1/2. Remember how sine works, right? Shall I make a little sine table here for us? It's easy to recall. Sine of 0 is 0, but when you go up to your first special angle, which is pi over 6, then it goes up to 1/2, right? Okay, and then what's the next special angle after pi over 6? As you're increasing your angles here, what's the next special angle after pi over 6?
Pi over 4.
Pi over 4, and what's the sine of pi over 4?
Square root of 2 over 2.
Square root of 2 over 2, and then what's the next special angle?
Pi over 3.
Pi over 3, and what is the what's the sine of pi over 3? This just keeps going up, right? So you have square root of 3 over 2, and then what's the of course 90 degrees is the last special angle. That's pi over 2, and that is 1. Right, sine of that is 1. By the way, you can think of this as the square root of 1 over 2 is 1/2. And you can think of this as the square root of 4 over 2, because square root of 4 is 2 over 2 is 1. See how that pattern goes up, right? 0, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, right? Okay. So it's easy to remember the sine values for special angles. Now, so of course, what we're interested in is 1/2, but we want the sine to be negative 1/2, darn it. So the answer is not, unfortunately, pi over 6, right? Okay, it's not pi over 6. So where are we going to get an angle? It's got to be related to pi over 6, right? But we want the sine to be negative 1/2, right? So where would that be? Well, it's got to be related to pi over 6. So what is what's another possibility here? I think it would be over there, right? Okay, this angle, whose reference angle is also pi over 6. But what angle is this that I've drawn? Can y'all read that?
I think it's 150 degrees.
Yes. Can you say that to me in radians? See, look, the way this works is, pi over 6 has sine of 1/2, right? So we're looking for another angle whose reference angle is pi over 6. Remember, reference angle is the angle between the x-axis and the angle. So you're looking for another angle whose reference angle is, I should draw it this way. You're looking for another angle whose reference angle is pi over 6. So that would be this angle, right? That's pi over 6 away from the x-axis. But you've got to measure that starting at the positive side of the x-axis. So what'd you say, Colin, that's going to be?
I just divided 150 by 30. And we got 5, right? So that's 5 pi over 6.
Yeah.
Is that close?
That is, but it's close. That's it. It's 5 pi over 6. See, the reason it's 5 pi over 6 is because you need an angle whose reference angle is pi over 6. So you need an angle that's pi over 6 away from the x-axis. So this angle over here in the second quadrant is pi over 6 away from the x-axis. But remember, you have to measure that angle starting at the positive side of the x-axis. So if this is pi over 6, then this part has to be 5 pi over 6, because when you add those together, you have to get a total of what? When you add this angle to this angle, you have to get a total of what? Pi, right? So 5 pi over 6 plus another pi over 6 would give you 6 pi over 6, which is pi. All right. But unfortunately, what is the sign of 5 pi over 6? Still not correct. Because in the second quadrant, what's the sign of sine? What's the SIGN of sine in the second quadrant? Remember, sine is related to the y-axis. What's the sign of the y-axis in the second quadrant? What's the sign of the y? Positive. So unfortunately, sine of 5 pi over 6 is still positive. So we want -1/2. Darn it. Okay, so we're going to have to keep going here. What's the next possibility? So what's the next angle? What's the next angle whose reference angle is pi over 6? It's this one, right? Okay, go pi over 6 below the x-axis. But what's that angle? So if you measure this starting here, going all the way around to here, what would that be?
Can you say 7 pi over 6?
7 pi over 6. Oh, finally we got an answer there. 7 pi over 6. 7 pi over 6. That's going to have negative sign, right? Okay, because this angle is below the x-axis. And so this part of the y-axis is negative, right? Where's the other possibility? It's got to be over here. This angle also has reference angle pi over 6. What's that angle? If you open all the way up like this, and you only leave pi over 6 left, what's that angle?
Can it be 11
Perfect.
pi
Yeah.
over 6?
Yeah, it's not 11, it's 11, Colin. Say it with confidence. Yeah.
11. 11.
All right. Okay. I'm just messing with you. All right. So it's 11 pi over 6. Yeah. There's the other possibility. All right. Now, you can I was going to say maybe you could find this. No, I don't think so. I think this you just have to think about carefully, okay, to find where sine of x is -1/2, right? Okay, it's going to be where sine has to be negative. Sine is negative in the second and the third and the fourth quadrants, right? Got to be below the x-axis because the sign of the SIGN of sine is associated with the y-axis. The y-axis is negative in the third and the fourth quadrants. So you have to find an angle in the third and the fourth quadrants whose reference angle is pi over 6, because it's sine of pi over 6, that's 1/2. So it's this angle that's pi over 6 here past the x-axis into the third quadrant, and then this angle that's just pi over 6 away from the x-axis over here in the fourth quadrant. So that's 7 pi over 6 and 11 pi over 6. All right. So there are the other two possible turning points at 7 pi over 6 and 11 pi over 6. Wow, great problem there. Okay. But only because finding sine of -1/2 was a little bit tricky. How much is 7 pi over 6? So can y'all calculate that for me? Or 11 pi over 6? Hope that matches our graph, or we've done this wrong. Can y'all do that for me? Is it that hard? 7 times pi divided by 6. Can't you do that on a calculator fast? 7 times pi divided by 6. I need to know approximately what that is, right? Because I don't know that off the top of my head. And I'm just trying to check the graph. I don't have enough light in here to run my calculator, so Oh, there it goes. So 7 times, well, I can't even find pi on the calculator.
It's about 3.665 around
3 point what?
3.665.
3.665. So about 3.67. Alva, this one, 3.67. And what's this one? 11 pi over 6. That's close to 2 pi. So that's close to 6. What's 11 pi over 6?
It was like
Wait,
five-
can't hear y'all. What?
It was about 5.76.
About 5. Is that what y'all got? 5.76? Someone else get that? So 3.67 and 5.76. Let's look on the graph and see if that's what we think. 3.67. So that must be 3.67. Oh, that's this one right here, right? And 5 points. Oh, that's this one right there, right? 5.76. Ah, okay. So very good. So it looks like the graph. It looks like the graph kind of confirms what we got there on paper. Okay. So now to find the y values, of course, you'd have to take these two and plug them back into your formula. All right. So I'll let y'all find the matching y values there because we've run out of time. Okay. All right. Now, so well, all right. So there you know how to find. You already sort of knew this, but there you know how to find possible turning points. Okay. But the only catch here is that, as we saw in the previous example, possible turning points don't have to turn out to be authentic turning points. You can have possible turning points that when you actually look at the graph, they turn out to not be turning points. Okay, so you get these sort of imposter turning points, okay, right, that aren't really turning points. So next time we're going to learn how do we figure out whether they're legitimate turning points or not, right? So we don't write down so we don't fool ourselves into thinking we have more turning points than we really have, okay? And then in that same process, we'll learn with pencil and paper how to figure out if a turning point is a local maximum or a local minimum, not just a turning point, but actually is it a local maximum or is it a local minimum, okay? So we just have to add a couple of steps to this process that we've just gone through, and we'll be able to answer those questions as well. Okay, it's actually pretty easy to do. All right. Okay, so well, we're out of time, so you've got to finish and turn in your test. So I'm gonna let you go. Then let me stop the recording. Remember, you got a homework due on Saturday night, right? So don't forget about that.